Imagine standing at the edge of everything you've ever known. Beyond this point, there's no sunlight warming your back, no familiar cosmic neighborhood, no protection from the vast wilderness of the galaxy. Now imagine a spacecraft no bigger than a small car, crossing that threshold alone, over 14 billion miles from home. What it found there wasn't just unexpected, it was shocking. The Voyager probes discovered something at the edge of our solar system that scientists are still trying to fully comprehend. If you're curious about these cosmic mysteries, make sure to subscribe to this channel and give a thumbs up. Now let's begin this journey. Voyager 1 has just become the first human-made object to leave our solar system and enter interstellar space. But what it encountered there was far more mysterious than anyone imagined. You see, space isn't empty. We often think of it as a void, a vacuum, nothingness between the stars, but that's not quite right. Space is filled with particles, magnetic fields, radiation, and energy. Near Earth, we're surrounded by a protective bubble called the heliosphere. This bubble is created by our sun. The sun doesn't just emit light, it constantly releases a stream of charged particles called the solar wind. These particles race outward in all directions at speeds exceeding 1 million miles per hour. They carry the sun's magnetic field with them, stretching it across billions of miles of space. This solar wind creates a protective cocoon around our entire solar system. It shields us from most of the cosmic radiation coming from deep space, from the violent deaths of distant stars, from the energetic remnants of supernovae that exploded thousands of years ago. Without this shield, life on Earth would face much higher levels of dangerous radiation. But this protection doesn't extend forever. Eventually, the solar wind runs into something. It collides with the interstellar medium, the matter that fills the space between stars. And where these two forces meet, something extraordinary happens. Think about blowing up a balloon inside a swimming pool. The air from your lungs pushes outward, creating a bubble. But the water pressure pushes back. Eventually, the balloon stops expanding. The air pressure inside equals the water pressure outside. The boundary between them is the balloon's surface. Our heliosphere works similarly, except instead of rubber, the boundary is made of invisible forces, clashing particles, and twisted magnetic fields. This boundary is called the heliopause, and it's here, at this cosmic shoreline, that Voyager made its most shocking discoveries. But before we dive deeper into what Voyager found, we need to understand the mission itself. The Voyager program began in 1977 during a rare alignment of the outer planets. Jupiter, Saturn, Uranus, and Neptune lined up in such a way that a spacecraft could visit all four using a technique called gravitational assist. Basically, each planet's gravity would fling the spacecraft toward the next one, like a cosmic slingshot. This alignment happens only once every 176 years. NASA knew they couldn't miss this opportunity. Two spacecraft were built, Voyager 1 and Voyager 2. They were twins carrying identical instruments, cameras to photograph distant worlds, spectrometers to analyze atmospheric composition, magnetometers to measure magnetic fields, plasma detectors to study charged particles, and perhaps most poignantly, each carried a golden record. This record contained sounds and images from Earth, music from different cultures, greetings in 55 languages, pictures of humans, animals, landscapes. It was a message in a bottle cast into the cosmic ocean, hoping that someday, perhaps millions of years from now, an alien civilization might find it and know that we existed. The primary mission was supposed to last just 5 years. Visit Jupiter and Saturn, take pictures, gather data, then quietly drift into the darkness as their power faded. But something remarkable happened. The spacecraft kept working. After Saturn, Voyager 2 continued to Uranus, arriving in 1986. Then on to Neptune in 1989, sending back the only close-up images we've ever had of these ice giants. Meanwhile, Voyager 1, having completed its planetary tour, headed straight out of the solar system, becoming the fastest moving human-made object at the time. By the early 2000s, both Voyagers were entering a region called the Helios Heath. This is the outer layer of the heliosphere, where the solar wind begins to slow down dramatically. Imagine a river approaching the ocean. The current slows, fresh water mixes with salt water, turbulence increases. The Helios sheath is like that transition zone. The solar wind, which has been racing outward at supersonic speeds, suddenly hits the resistance of the interstellar medium. It slows down, becomes turbulent, and starts behaving in unpredictable ways. Scientists expected this region to be relatively calm. They thought the transition from solar influence to interstellar space would be gradual. They were wrong. Voyager 1 began detecting strange phenomena. The cosmic ray intensity started increasing. These cosmic rays are high-energy particles from outside our solar system, accelerated to nearly the speed of light by distant supernova and other violent cosmic events. Inside the heliosphere, they're mostly blocked by the solar wind. But as Voyager approached the heliopause, more and more of them penetrated through. Then something truly bizarre happened. In 2012, several months before Voyager 1 crossed the heliopause, it detected sudden increases in cosmic ray intensity. These spikes lasted for days, then subsided. Scientists were puzzled. What could cause such rapid changes? Further analysis revealed something shocking. The magnetic field during these events still pointed in the direction associated with the solar magnetic field, not the interstellar magnetic field. It was as if Voyager had briefly peeked beyond the boundary, then stepped back. Years later, scientists developed a theory. Voyager had encountered what they called magnetic flux tubes. These are like tunnels of interstellar magnetic field that had pushed into the Helios sheath. Imagine fingers of the ocean reaching into the beach during high tide. These flux tubes brought with them cosmic rays from interstellar space, giving Voyager a preview of what lay ahead. But the spacecraft was still technically inside the heliosphere. The full crossing was yet to come. On August 25, 2012, everything changed. Voyager 1's instruments detected a dramatic shift. The intensity of solar wind particles dropped to nearly zero. At the same time, cosmic ray intensity jumped to levels never before recorded by the spacecraft. The magnetic field orientation remained surprisingly stable, but something fundamental had transformed. Voyager 1 had crossed the heliopause. After traveling for 35 years, covering over 11 billion miles, humanity's most distant ambassador had finally left home. But here's where the story gets truly fascinating. When Voyager 1 sent its data back to Earth, traveling at the speed of light for over 17 hours to reach NASA's antennas, scientists discovered something nobody predicted. The temperature at the heliopause wasn't what their models suggested. The boundary between the solar wind and interstellar medium should have been relatively cool, maybe a few thousand degrees. Instead, Voyager detected temperatures exceeding 50,000 degrees Fahrenheit. Some measurements suggested even higher values approaching 54,000 degrees. Let that sink in for a moment. We're talking about a region of space that should be cold and empty, yet it's hotter than the surface of many stars. How is this possible? The answer lies in the violent collision between two cosmic winds. When the solar wind particles, traveling at over 1 million miles per hour, slam into the interstellar medium, they don't just stop. They create a shock wave, similar to a sonic boom when an aircraft breaks the sound barrier. This shock heats the particles to extreme temperatures, but temperature in space doesn't work the way it does on Earth. When we say the heliopause is 50,000 degrees, we're measuring the energy of individual particles. However, space is so empty that there are very few particles in any given volume. If you were standing at the heliopause in a spacesuit, you wouldn't burst into flames. There aren't enough hot particles to transfer significant heat to your body. It's like the difference between a single spark and a bonfire. The spark might be hotter, but the bonfire has more total heat energy. This discovery revealed something profound about our cosmic neighborhood. The boundary of our solar system isn't a gentle transition, it's a violent, energetic frontier. The sun's influence extends so far that even at distances where sunlight is barely a faint glow, its wind is still powerful enough to create temperatures that rival stellar surfaces. We're protected by a bubble of energy far more dynamic than anyone imagined. 6 years later, on November 5, 2018, Voyager 2 followed its twin across the threshold. But its crossing revealed even more surprises. While Voyager 1 had detected those mysterious magnetic flux tubes months before crossing, Voyager 2 experienced no such precursors. One day it was in the heliosheath, the next it was in interstellar space. The transition was sharp and clean. Why were the two crossings so different? The answer has to do with where each spacecraft crossed. Voyager 1 went through the heliopause in the northern hemisphere of the heliosphere, while Voyager 2 crossed in the southern hemisphere. Just as Earth's northern and southern hemispheres experience different weather patterns, the heliosphere's two halves behave differently. The Sun's magnetic field has a northern and southern component, and these interact with the interstellar medium in distinct ways. What's truly remarkable is that both spacecraft are still functioning. Think about this for a second. These machines were built in the 1970s, during the era of 8-track tapes and rotary phones. Their computers have less processing power than a modern key fob for your car. Each carries only about 68 kilobytes of memory. Your smartphone has millions of times more storage capacity. Yet they continue to operate in the harshest environment imaginable, bombarded by cosmic radiation, subjected to extreme cold, billions of miles from any hope of repair. They're powered by radioisotope thermoelectric generators, essentially nuclear batteries. These devices convert heat from radioactive decay into electricity. When Voyager launched, each spacecraft generated about 470 watts of power. That's less than a typical hairdryer. Now, nearly 50 years later, their plutonium fuel has decayed significantly. Each spacecraft produces less than 250 watts. NASA engineers have had to make difficult decisions about which instruments to keep running and which to shut down to conserve power. Speaking of the incredible distances involved in the challenges of space travel, if you're wondering about humanity's future beyond our solar system and the enormous obstacles we face, I actually made an entire video exploring exactly that. It's called "This is Why We Are Stuck in the Solar System Forever," and it dives deep into the physics, engineering, and cosmic barriers that make interstellar travel so incredibly difficult. The same forces that Voyager is measuring at the heliopause are part of what makes leaving our solar system such a monumental challenge for human travelers. You'll find it really complements what we're discussing here. The link is in the description and pinned on the comments. Every piece of data the Voyagers send back is precious. Currently, it takes over 22 hours for a signal from Voyager 1 to reach Earth. That's because it's traveling at the speed of light across more than 15 billion miles of space. When engineers send a command to the spacecraft, they wait 22 hours for it to arrive, then another 22 hours to confirm it worked. A simple software update becomes a 2-day process. Imagine troubleshooting a computer problem with a 44-hour delay between each action and response. Yet despite these challenges, the data keeps flowing. And what it's revealing about interstellar space is reshaping our understanding of the galaxy. One of the most significant discoveries involves cosmic rays. Before Voyager, scientists knew that cosmic rays were high-energy particles from beyond our solar system, but they didn't know exactly how the heliosphere blocked them. Now we have direct measurements from both sides of the boundary. Inside the heliosphere, cosmic ray intensity is relatively low. The solar wind acts like a shield, deflecting most of these particles. But the moment Voyager 1 crossed the heliopause, cosmic ray intensity increased by about 9%. That might not sound like much, but it represents millions of additional high-energy particles hitting the spacecraft every second. These particles come from supernova remnants, exploding stars that died thousands or millions of years ago. Their deaths scattered matter across the galaxy at relativistic speeds, creating a background radiation that permeates interstellar space. What shocked scientists even more was the discovery of a magnetic barrier just inside the heliopause. Voyager 2 detected this feature clearly. In this region, spanning several astronomical units, the magnetic field strength increases significantly. It's as if the interstellar magnetic field is pushing against the heliosphere, compressing the solar magnetic field into a denser barrier. This compression creates a partial shield that helps protect the inner solar system from some of the cosmic rays trying to enter. Think of it like a castle with multiple walls. The heliosphere is the outer wall created by the solar wind. The magnetic barrier is an inner reinforcement where the solar and interstellar magnetic fields press against each other. Together, these structures protect Earth and the other planets from the full intensity of galactic cosmic radiation. Without them, the radiation environment on Earth would be significantly harsher, potentially affecting the evolution of life itself. But here's a troubling thought. The Sun's activity varies over time. During solar maximum, when the Sun is most active, the solar wind is stronger and the heliosphere extends farther. During solar minimum, the Sun is quieter, the solar wind weakens, and the heliosphere contracts. Right now, we're measuring the heliosphere during a relatively average period of solar activity. But what happens during a deep solar minimum? Could the heliosphere shrink so much that more cosmic rays reach Earth? Scientists are actively researching this question. There's evidence from ice cores and tree rings suggesting that Earth's cosmic ray exposure has varied over thousands of years. These variations correlate with changes in solar activity. Some researchers theorize that increased cosmic ray intensity might affect cloud formation in Earth's atmosphere, potentially influencing climate. Others suggest it could impact atmospheric chemistry or even the rate of genetic mutations in living organisms. The Voyager discoveries have also revealed something unexpected about the shape of the heliosphere. Scientists originally thought it would be comet-shaped, with a long tail streaming behind as the solar system moves through interstellar space. Our Sun orbits the center of the Milky Way at about 450,000 miles per hour, so naturally there should be a directional flow, right? But data from both Voyagers, combined with observations from the IBEX satellite, which images the heliosphere from Earth orbit, suggest the structure is more complex. The heliosphere appears to be more rounded than expected, almost spherical rather than elongated. This suggests that the interstellar magnetic field pressing against it is stronger than scientists predicted. The magnetic pressure from outside nearly balances the pressure from the solar wind pushing outward. It's like two opposing forces in equilibrium, creating a bubble rather than a teardrop. This discovery has forced researchers to reconsider their models of how our solar system interacts with the galaxy around it. But perhaps the most profound implication of Voyager's discoveries involves something we can't directly measure: the nature of the interstellar medium itself. For the first time in human history, we have instruments physically present in the space between stars. Everything we knew about interstellar space before Voyager came from remote observations, light collected by telescopes, radio waves detected from Earth. Now we have direct measurements, and they're telling us that interstellar space is far from uniform. The region immediately outside the heliopause is called the very local interstellar medium. It's the neighborhood of the galaxy that our solar system is currently passing through. Voyager's instruments measure its temperature, density, magnetic field strength, and composition. The temperature is surprisingly warm, around 13,000 degrees Fahrenheit for the neutral atoms. Again, this doesn't mean it would feel hot, because the particle density is incredibly low, but it tells us that this region has been heated by something, possibly by shock waves from nearby supernova explosions that occurred millions of years ago. The density is also higher than some predictions suggested. Voyager 2 detected about 0.04 atoms per cubic centimeter in the very local interstellar medium. That might sound empty, and it is by Earth standards. The best vacuum we can create in laboratories on Earth still contains billions more particles per cubic centimeter. But in the vast emptiness of space, this density is significant. It means there's enough matter between the stars to interact with, to shape stellar winds, to form clouds that eventually collapse into new stars and planets. The magnetic field strength measured by Voyager is particularly intriguing. It's stronger than scientists expected, about 5 microgauss. For comparison, Earth's magnetic field at the surface is about half a Gauss, roughly 100,000 times stronger. But out there, billions of miles from any star, a magnetic field of 5 microgauss is surprisingly robust. This field doesn't come from any single source. Instead, it's a complex tapestry woven by ancient supernova explosions, stellar winds from countless stars, and the rotation of the galaxy itself. Understanding this magnetic field is crucial because it influences how cosmic rays propagate through the galaxy. These charged particles don't travel in straight lines. They spiral along magnetic field lines, bouncing and scattering in complex patterns. The stronger the magnetic field, the more confined and directed their paths become. By measuring the interstellar magnetic field directly, Voyager is helping scientists understand how radiation spreads through the galaxy and how it might affect planetary systems like ours. Now here's where things get even more fascinating. Voyager isn't just measuring what's around it right now. It's also hearing sounds from deep space. Well, not sounds exactly, because sound can't travel through the vacuum of space. But Voyager's plasma wave instrument detects oscillations in the plasma, the ionized gas that fills interstellar space. These oscillations occur at frequencies that, if converted to audio, would be in the range humans can hear. When scientists converted these plasma oscillations to sound, they discovered something beautiful and eerie. Interstellar space hums with a faint, persistent tone. It's not random noise, it's a coherent frequency, like a single note played on an impossibly vast instrument. This tone comes from the vibration of electrons in the interstellar plasma, oscillating at a rate determined by the plasma's density. By measuring this frequency, scientists can calculate exactly how many electrons are present in any given volume of space. But occasionally, this steady hum is interrupted by something more dramatic. When the sun releases a particularly powerful burst of solar wind, perhaps from a coronal mass ejection, the disturbance propagates outward like ripples on a pond. Months or even years later, this disturbance reaches Voyager's location, billions of miles away. The spacecraft's instruments detect a sudden increase in plasma oscillation frequency, a brief, higher-pitched tone cutting through the background hum. These events are like messages from the sun reaching out across interstellar space, reminding us that even in the darkness between stars, our home star's influence can still be felt. One of the most poignant aspects of the Voyager mission is its impermanence. These spacecraft won't last forever. Their power is declining by about 4 watts per year. By the early 2030s, they'll no longer have enough electricity to power any scientific instruments. The last signals will be sent. The last data will be received and then silence, but the spacecraft themselves will continue their journeys. They'll coast through the void for millennia, perhaps for millions of years, gradually drifting farther from Earth. In about 40,000 years, Voyager 1 will pass within about 1.6 light-years of a star called Gliese 445. It's a red dwarf in the constellation Camelopardalis, invisible to the naked eye from Earth. But from Voyager's future vantage point, it will be the closest star. The spacecraft will sail past silently, its instruments long dead, its golden record still spinning slowly in the darkness, carrying humanity's message to anyone who might find it. Voyager 2's trajectory is different. In roughly 40,000 years, it will pass near a star called Ross 248, another red dwarf, this one in the constellation Andromeda. Then, in about 296,000 years, it will approach Sirius, the brightest star in Earth's night sky. By that time, humanity might be extinct, or we might have spread across the galaxy, or we might have transformed into something unrecognizable. But Voyager will still be there, a monument to a species that looked up at the stars and wondered what lay beyond. The longevity of these spacecraft is genuinely remarkable. They were built during an era when space exploration was young, when every mission was an experiment, when engineers didn't have decades of spaceflight experience to draw upon. Yet the Voyagers have outlasted nearly every other deep space probe. Part of this success comes from clever engineering. The spacecraft were overbuilt with redundant systems and robust components, but part of it is simply luck. They avoided catastrophic impacts with debris. Their electronics withstood radiation that might have destroyed less fortunate probes. There's something deeply moving about the Voyager mission. These machines represent humanity at its best. They embody curiosity, ingenuity, perseverance, and hope. They were launched during the Cold War, a time of tension and fear, yet they carried a message of peace and welcome. The golden records include greetings in languages from every inhabited continent. They feature music from diverse cultures: Bach, Beethoven, Chuck Berry, traditional songs from Peru, Zaire, India, Japan. They show images of humans in all our diversity, along with pictures of animals, plants, landscapes, and the pale blue dot we call home. Carl Sagan, who chaired the committee that selected the contents of the Golden Record, wrote beautifully about what these spacecraft mean. He described them as a token of our sounds, our science, our images, our music, our thoughts, and our feelings. He hoped that any civilization that might eventually find them would understand that we were a species capable of great achievements, that we looked beyond our own small world, that we reached out across the cosmic ocean with friendship and wonder. But the Voyager mission also reminds us of our limitations. These spacecraft, traveling faster than anything humans have ever built, cover only about 3.6 astronomical units per year. An astronomical unit is the distance from Earth to the Sun, about 93 million miles, so Voyager 1 travels roughly 335 million miles annually. That sounds fast, and it is by human standards, but the nearest star system, Alpha Centauri, is over 4 light-years away. At Voyager's current speed, it would take about 75,000 years to reach it if it were heading in that direction, which it's not. This is the harsh reality of interstellar travel. Space is unimaginably vast. The distances between stars are so enormous that even traveling at tens of thousands of miles per hour feels like crawling. The galaxy is about 100,000 light-years across. Light, the fastest thing in the universe, takes 100,000 years to travel from one side to the other. Voyager, moving at a tiny fraction of light speed, would take billions of years to cross the galaxy, far longer than the current age of the universe. Yet despite these humbling distances, Voyager has achieved something extraordinary. It has shown us that interstellar travel is possible, at least for robotic emissaries. It has proven that we can build machines capable of operating in the space between stars, and it has given us our first direct glimpse of the galactic environment that surrounds our solar system. Every piece of data it sends back expands our understanding of the universe and our place within it. The discoveries at the Heliopause have also raised new questions. Scientists now want to know how the heliosphere changes over time. Does it pulse with the solar cycle? Does it respond to changes in the interstellar medium as the solar system moves through different regions of the galaxy? To answer these questions, NASA and other space agencies are planning new missions. The Interstellar Mapping and Acceleration Probe, IMAP, launched in 2025, is studying the heliosphere from Earth orbit, building on the work of its predecessor, IBEX. But there's growing interest in sending another probe beyond the Heliopause, one specifically designed for interstellar science. Voyager was built to study planets, and its journey into interstellar space was almost an afterthought. Imagine what we could learn with a spacecraft designed from the beginning to study the boundary of the solar system and the space beyond. It could carry instruments optimized for measuring plasma properties, magnetic fields, neutral atoms, and cosmic rays. It could potentially reach the heliopause faster than Voyager by using more advanced propulsion systems or gravitational assists from multiple planets. One proposed mission concept is called the Interstellar probe. Engineers and scientists have been designing this spacecraft for years, debating the best trajectory, the ideal instruments, and the power systems needed for decades of operation. Some proposals suggest using nuclear electric propulsion, which could accelerate the spacecraft to speeds 2 or 3 times faster than Voyager. Others advocate for a close solar flyby, diving near the Sun to use its gravity as a slingshot, potentially reaching even higher velocities. The challenge with any interstellar mission is time. Even with advanced propulsion, reaching the heliopause would take at least 15 to 20 years. That means the scientists who design the mission might not live to see its most important discoveries. The engineers who build it would be retired by the time it crosses the boundary. This requires a special kind of vision, a willingness to work on something whose payoff extends beyond one's own lifetime. It's the opposite of our modern culture of instant gratification. It's science for the ages. But the potential rewards are immense. An interstellar probe could map the three-dimensional structure of the heliosphere, revealing how it varies with latitude and longitude. It could measure the composition of interstellar dust grains, telling us what materials exist between the stars and how they differ from the dust in our solar system. It could detect neutral hydrogen atoms that pass through the heliosphere, giving us clues about the density and temperature of the galaxy's interstellar medium farther from the Sun. Perhaps most exciting, it could help us understand how our solar system fits into the broader galactic environment. You see, the Sun isn't stationary. It orbits the center of the Milky Way, completing one circuit every 225 million years. During this orbit, it passes through different regions of the galaxy. Sometimes it travels through dense clouds of gas and dust. Other times, it moves through clearer regions. These variations affect the heliosphere's size and shape, which in turn influences the amount of cosmic radiation reaching Earth. There's evidence that Earth's climate has been affected by our journey through the galaxy. Some ice age periods coincide with times when the solar system was passing through denser regions of the interstellar medium. The theory is that increased cosmic ray intensity during these periods could have affected cloud formation, potentially cooling the planet. This connection between cosmic rays and climate is controversial and not fully proven, but it highlights how interconnected everything is. We're not isolated on our little planet. We're part of a solar system, which is part of a galaxy, which is part of a universe, and all these scales influence each other. Voyager's discoveries have also had practical implications for understanding space weather. The Sun constantly releases particles and radiation that can affect satellites, power grids, and communication systems on Earth. By studying how the solar wind behaves at different distances from the Sun, scientists can build better models to predict space weather events. The magnetic barrier that Voyager 2 discovered near the heliopause, for instance, tells us about how shock waves from powerful solar storms propagate through the heliosphere. This knowledge helps protect our technology from potentially damaging solar events. Another fascinating aspect of Voyager's journey involves time itself. Due to the effects of special relativity, time moves slightly differently for the spacecraft than it does for us on Earth. Voyager is moving at about 38,000 miles per hour relative to the Sun. At this speed, time dilation is incredibly tiny, less than 1 second over the entire mission, but it's still real and measurable. Every clock on Voyager, including the radioactive decay of its plutonium power source, runs ever so slightly slower than identical clocks on Earth. This effect becomes more pronounced at higher speeds. If we could build a spacecraft that traveled at 10% of light speed, time dilation would become significant. A journey to the nearest star might take 40 years from Earth's perspective, but only 39 years for the spacecraft's onboard clocks. At 50% of light speed, the difference becomes dramatic. At 90% of light speed, time slows so much that decades could pass on Earth while only years pass for the spacecraft. These aren't science fiction fantasies. They're real consequences of Einstein's relativity, proven by countless experiments. But achieving such speeds presents enormous challenges. Voyager's velocity came from gravitational assists and a relatively small rocket. To reach even 1% of light speed, we'd need propulsion systems far beyond our current technology. Nuclear fusion rockets, antimatter engines, or laser-powered light sails have all been proposed. Each has theoretical advantages and practical problems. Fusion requires us to master controlled fusion reactions, something we haven't yet achieved despite decades of research. Antimatter is incredibly difficult to produce and store. Light sails work in theory but require enormous laser arrays to push them to high speeds. There's also the problem of radiation. At high velocities, even individual hydrogen atoms become dangerous. When you're traveling at a significant fraction of light speed, colliding with a single proton releases energy comparable to a bullet. The interstellar medium, sparse as it is, becomes a hazardous environment. Any future fast interstellar spacecraft would need heavy shielding, which adds mass, which requires more energy to accelerate. It's a vicious cycle that makes interstellar travel extraordinarily difficult. Yet Voyager shows us that slow and steady can still accomplish incredible things. These spacecraft weren't designed to be fast. They were designed to last, to survive, to keep transmitting data year after year, and they've succeeded beyond anyone's wildest expectations. Their journey teaches us that patience and persistence can overcome seemingly impossible obstacles. You don't need to move at relativistic speeds to explore the universe. You just need to keep going, 1 mile at a time, 1 day at a time, for decades, if necessary. The images Voyager sent back during its planetary encounters changed how we see the solar system. Jupiter's swirling clouds, photographed in stunning detail. Io's active volcanoes, the first ever discovered beyond Earth. Saturn's rings, revealed as intricate structures made of countless ice particles. Titan's thick atmosphere, hiding a surface we couldn't see. Uranus's tilted rotation, spinning on its side like a rolling ball. Neptune's great dark spot, a storm larger than Earth. Miranda's bizarre terrain, looking like a moon shattered and reassembled. Triton's nitrogen geysers, erupting through an icy crust. Each of these discoveries expanded our understanding of planetary science. We learned that moons could be geologically active, heated by tidal forces from their parent planets. We discovered that giant planets have complex atmospheric dynamics, with storms that persist for centuries. We found that ring systems are common, delicate, and temporary on geological timescales. We realized that the outer solar system is far more diverse and interesting than anyone imagined. But perhaps the most iconic image Voyager ever captured wasn't of a distant planet. It was of Earth itself. In 1990, as Voyager 1 was leaving the planetary region, Carl Sagan convinced NASA to turn its camera back toward home. From nearly 4 billion miles away, Earth appeared as a tiny point of light, less than a single pixel, suspended in a beam of scattered sunlight. Sagan called it the pale blue dot, and he wrote eloquently about what it meant. "Look again at that dot," he said. "That's here, that's home, that's us. On it, everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives. The aggregate of our joy and suffering, thousands of confident religions, ideologies, and economic doctrines, every hunter and forager, every hero and coward, every creator and destroyer of civilization, every king and peasant, every young couple in love, every mother and father, hopeful child, inventor and explorer, every teacher of morals, every corrupt politician. Every superstar, every supreme leader, every saint and sinner in the history of our species lived there on a mote of dust suspended in a sunbeam. This perspective, this cosmic viewpoint, is perhaps Voyager's greatest gift to humanity. It shows us how small we are, how fragile, how temporary, but it also shows us how precious. We're the only known intelligence in the universe, the only beings capable of understanding the cosmos and our place in it. We're made of atoms, forged in the hearts of dying stars, rearranged through billions of years of evolution into creatures that can contemplate our own existence. We're the universe becoming aware of itself. Voyager's journey reminds us that we're all connected, not just to each other, but to everything. The oxygen you breathe was created by massive stars that exploded before our solar system formed. The calcium in your bones came from supernova explosions. The iron in your blood was forged in stellar cores under temperatures and pressures we can barely imagine. You are, quite literally, made of stardust. And so is everything else on Earth, every mountain, every ocean, every tree, every animal. This connection extends beyond Earth. The same physical laws that govern atoms on our planet apply everywhere in the universe. The same forces that hold your body together also hold stars together. The same gravity that keeps you planted on the ground also keeps galaxies from flying apart. When you look at distant stars, you're seeing light that left them years, decades, or even centuries ago. You're literally looking back in time, seeing the universe as it was, not as it is now. Voyager's instruments measure this universe directly. Every data point it transmits is a piece of cosmic truth, a fact about reality that existed long before humans evolved and will continue long after we're gone. The magnetic field, strength at the heliopause, doesn't care about human politics or economics. The temperature of the interstellar medium isn't influenced by our beliefs or opinions. These are objective properties of the universe, waiting to be discovered, regardless of who discovers them or when. This is the power of science. It's a method for finding truth that transcends individual perspectives. A scientist in Brazil, another in Japan, and a third in Norway can all measure the same phenomenon and get the same results. They might speak different languages, practice different religions, and hold different political views, but the data doesn't change. The universe operates according to consistent principles, and science is our tool for uncovering them. Voyager embodies this scientific spirit. It's a machine built by thousands of people from many nations, all working toward a common goal: understanding the cosmos. Engineers designed its structure, scientists selected its instruments, technicians assembled its components, mathematicians calculated its trajectory, and now, decades later, researchers around the world analyze its data, publishing papers, debating interpretations, building upon each other's work. The data from Voyager has generated hundreds of scientific papers. Each new discovery prompts new questions. Why is the heliopause temperature so high? What causes the variations in cosmic ray intensity? How does the interstellar magnetic field connect to the larger galactic magnetic field? Why did Voyager 1 and Voyager 2 observe different precursor phenomena before crossing the heliopause? These questions drive ongoing research and inspire new missions. One particularly intriguing mystery involves something called the hydrogen wall. Before Voyager reached the heliopause, the Hubble Space Telescope detected ultraviolet light from a region beyond the heliosphere. This light suggested the presence of a dense accumulation of hydrogen atoms piled up where the solar wind meets the interstellar medium. Scientists predicted Voyager would pass through this hydrogen wall and measure its properties directly. But the data has been ambiguous. Some measurements support the hydrogen wall's existence, while others suggest it might be more diffuse than expected. This uncertainty is typical of science at the frontier of knowledge. Initial observations raise questions, predictions are made, new data arrives. Sometimes it confirms expectations, sometimes it doesn't. The process is messy, complicated, and beautiful. It's how we learn, how we refine our understanding, how we gradually construct a more accurate picture of reality. Another unresolved question concerns the exact shape and extent of the heliosphere. We know it's roughly spherical, but where does it end? how far does the sun's influence truly extend? Beyond the heliopause, there's a region called the bow shock, where the interstellar medium piles up as it flows around the heliosphere. At least, that's what theory predicts. But recent observations suggest the bow shock might not exist, or it might be much weaker than expected. This would mean the interstellar medium flows around the heliosphere more smoothly than scientists thought. Understanding these details matters because they affect how we think about other stars and their planetary systems. Every star with a stellar wind creates its own version of a heliosphere. These stellar bubbles interact with the interstellar medium in complex ways. If two stars pass close to each other, their heliospheres might overlap, potentially affecting the planets orbiting those stars. Imagine if another star passed through our solar system. Its stellar wind could compress our heliosphere, allowing more cosmic radiation to reach Earth. This scenario isn't just hypothetical. Roughly 70,000 years ago, a red dwarf called Schultz's star passed through the Oort cloud, the distant region of icy bodies that surrounds our solar system. It came within about 1 light-year of the Sun, much closer than any star has approached since. Did its passage affect our heliosphere? Did cosmic ray intensity increase on Earth? We don't have direct measurements from that time, but ice core data might contain clues. Scientists are investigating whether anomalies in isotope ratios from that period could indicate a temporary increase in cosmic radiation. These connections between stellar encounters and terrestrial effects are part of a broader field called astrobiology. This discipline studies how life arises, evolves, and persists in the universe. One major question is how cosmic radiation affects the evolution of life. On one hand, radiation causes mutations, most of which are harmful. Too much radiation could sterilize a planet, preventing complex life from evolving. On the other hand, mutations are the raw material of evolution. Without them, life couldn't adapt to changing environments. There might be an optimal level of cosmic radiation, high enough to drive evolution, but low enough not to be lethal. Earth's heliosphere, along with our magnetic field and atmosphere, maintains this balance. The Sun shields us from most galactic cosmic rays. Earth's magnetic field deflects charged particles, creating the beautiful auroras when some particles funnel down near the poles. Our atmosphere absorbs the remaining radiation, preventing most of it from reaching the surface. This multi-layered protection system has existed for billions of years, allowing life to flourish and evolve. But this protection varies over time. When the Sun is more active, the heliosphere expands, blocking more cosmic rays. When the Sun is quieter, the heliosphere shrinks, letting more through. Earth's magnetic field also changes. It's reversed many times throughout Earth's history, with north and south magnetic poles flipping. During these reversals, which take thousands of years, the magnetic field temporarily weakens, offering less protection from cosmic radiation. Some researchers have looked for correlations between magnetic reversals and extinction events in the fossil record. The evidence is inconclusive, but it's a reminder that we're vulnerable to cosmic influences. Voyager's measurements help us understand these protective systems better. By knowing the baseline cosmic ray intensity outside the heliosphere, scientists can calculate how much radiation the heliosphere blocks. By measuring how the heliopause responds to solar activity, they can model how radiation exposure varies over solar cycles. This information is crucial for planning future human missions beyond Earth's protective bubble. Astronauts on the International Space Station already experience higher radiation doses than people on the ground. They're above most of the atmosphere, so they're exposed to more cosmic rays and solar particles. On a journey to Mars, astronauts would be even more vulnerable. They'd spend months in deep space, beyond Earth's magnetic field, with only their spacecraft hull for protection. The radiation dose on such a trip could significantly increase cancer risk. Understanding the radiation environment throughout the solar system is essential for protecting future space travelers. Voyager has also taught us about the resilience of technology in extreme environments. The spacecraft operates at temperatures near absolute zero. Its electronics are bombarded by radiation constantly. Micrometeorites occasionally strike its surfaces, yet it keeps functioning. This resilience comes from careful design, radiation-hardened components, and redundant systems. But it also comes from simplicity. Voyager doesn't have complex software that could crash or intricate mechanisms that could jam. Its design philosophy was robustness over sophistication. Modern spacecraft are far more capable than Voyager. They carry better cameras, more sensitive instruments, and more powerful computers, but they're also more complex, with more potential failure points. There's a trade-off between capability and reliability. The James Webb Space Telescope, for instance, is incredibly sophisticated, but it required years of development and testing to ensure it would work correctly. Even so, engineers were nervous during its deployment because so many things had to go right. Voyager's success suggests that for certain missions, especially long-duration exploration, simpler might be better. The Interstellar probe concept includes discussions about how complex to make the spacecraft. Should it have sophisticated artificial intelligence to respond to unexpected situations? Or should it be relatively simple, relying on pre-programmed commands from Earth? The answer depends on the mission's goals, the available technology, and the acceptable level of risk. Another lesson from Voyager involves the importance of flexibility. The spacecraft wasn't designed to explore interstellar space, yet it's provided groundbreaking interstellar data. This happened because NASA kept supporting the mission, funding operations decades after the original objectives were met. Many missions end when their primary goals are accomplished, even if the spacecraft could continue. Voyager shows the value of extended missions, of continuing to operate functional spacecraft as long as possible. This philosophy has become more common. The Opportunity rover on Mars, designed for a 90-day mission, operated for almost 15 years. The Cassini spacecraft, after completing its primary mission at Saturn, continued for 13 additional years through multiple mission extensions. These extended operations have provided some of the most exciting discoveries, observations that weren't possible during the initial mission phases. The human element of the Voyager mission is equally remarkable. When Voyager launched in 1977, the engineers working on it were young professionals, fresh out of university, excited about space exploration. They've now spent their entire careers with these spacecraft. Some have retired, others have passed away, but many remain involved, their expertise irreplaceable. These engineers know Voyager's quirks, its history, its peculiarities in ways that can't be fully documented or transferred to younger team members. This institutional knowledge is precious. When Voyager 1 experienced a computer glitch in 2018, causing it to send corrupted data, the team had to diagnose the problem from billions of miles away. They couldn't just reboot the computer like you might with your laptop. Any command sent took over 19 hours to arrive. If they made a mistake, they might permanently damage the spacecraft. The engineers had to remember how the onboard computers were programmed, understand the architecture designed decades earlier, and devise a solution using systems built before modern computing existed. They succeeded. They identified that one of the spacecraft's 3 onboard computers had corrupted data in its memory. They sent commands to switch to a backup computer, one that hadn't been used in years. The process took weeks of careful work, with each command carefully tested and reviewed before transmission. But eventually, Voyager 1 resumed sending scientific data. This success demonstrated not just technical skill, but deep dedication. These engineers care about Voyager not as a machine, but as something almost alive, a distant explorer that depends on them for survival. This relationship between humans and their robotic emissaries is a recurring theme in space exploration. The rovers on Mars develop personalities in the minds of their operators. Scientists feel genuine emotion when missions end. There were tears at mission control when Cassini plunged into Saturn's atmosphere, deliberately destroying itself to avoid contaminating Saturn's potentially habitable moons. The spacecraft had become, in a sense, a colleague, a partner in exploration. Voyager evokes even stronger emotions because of its sheer distance and longevity. It's humanity's farthest-reaching creation, our most distant representative. Every signal it sends is a reminder that we're capable of incredible achievements when we work together toward ambitious goals. In an era often characterized by division and short-term thinking, Voyager stands as a testament to long-term vision, international cooperation, and the pursuit of knowledge for its own sake. The golden records on both Voyager spacecraft amplify this emotional resonance. These records contain 115 images, natural sounds like thunder, wind, and animal calls, musical selections from various cultures, and greetings in 55 languages. Carl Sagan and his team carefully selected each element to represent humanity's diversity and achievements. They included images of human anatomy, mathematical definitions, chemical formulas, and diagrams showing Earth's location in the galaxy. The chances of an alien civilization finding these records are astronomically small. Space is so vast that Voyager could travel for billions of years without passing near another star system. Even if it did, the probability of an intelligent civilization finding a small spacecraft in the emptiness between stars is essentially zero. The golden records are more symbolic than practical, a message we're sending as much to ourselves as to hypothetical aliens. What does the golden record say about us? It says we're a species that makes music, that we value art and beauty. It says we're diverse, with many languages and cultures. It says we understand science and mathematics, that we've figured out the fundamental laws governing reality. It says we're optimistic enough to believe that somewhere out there, other minds might exist, other beings who look up at their night sky and wonder if they're alone. But the golden record also reveals what we choose to hide. There are no images of war, poverty, or environmental destruction, no sounds of arguments or crying. The music is universally uplifting or contemplative, never angry or discordant. We're presenting an idealized version of humanity, our best face forward. Is this dishonest, or is it simply showing what we aspire to be, even if we don't always live up to those aspirations? Carl Sagan defended these choices by arguing that the record represents our potential, not just our reality. Yes, humans are capable of violence and cruelty, but we're also capable of incredible compassion, creativity, and cooperation. The golden record emphasizes the latter because that's the humanity worth celebrating, the version of ourselves we hope will endure and eventually reach the stars. The record also includes personal messages. President Jimmy Carter wrote, "This is a present from a small, distant world, a token of our sounds, our science, our images, our music, our thoughts, and our feelings. We are attempting to survive our time so we may live into yours." Kurt Waldheim, then Secretary General of the United Nations, added, "We step out of our solar system into the universe, seeking only peace and friendship, to teach if we are called upon, to be taught if we are fortunate." These messages are poignant because they acknowledge uncertainty. Attempting to survive our time recognizes that humanity faces existential risks. Nuclear war was a very real possibility in 1977, as it remains today. Climate change, pandemics, asteroid impacts, and artificial intelligence all pose potential threats to our civilization. The golden record is, in part, a time capsule. If humanity doesn't survive, at least some record of our existence will persist, drifting through the galaxy long after Earth has become a lifeless rock. But there's also hope in these messages. Seeking peace and friendship expresses the possibility that we might overcome our divisions and destructive tendencies. Space exploration requires cooperation on a scale that transcends national boundaries. The International Space Station, for example, brings together astronauts and scientists from countries that have been historical rivals. When you're orbiting Earth at 17,500 miles per hour, seeing borders vanish beneath you, national conflicts seem petty and temporary. Voyager was built during the Cold War, a time when the United States and Soviet Union competed fiercely in space. The space race was as much about demonstrating technological superiority as scientific discovery. Yet both nations knew that space exploration was ultimately a human endeavor, not just a national one. The Golden Record includes greetings in Russian alongside English, Chinese, Spanish, and dozens of other languages. It's a tacit acknowledgement that we're all one species, sharing one small planet. As Voyager continues its journey, it carries with it not just scientific instruments, but also our dreams and aspirations. It represents the explorer's spirit that drove humans to cross oceans, climb mountains, and venture into the unknown throughout our history. This drive to explore seems fundamental to human nature. We're not content to stay in one place. We want to see what's over the next hill, beyond the next horizon, on the other side of the cosmic ocean. Some philosophers and scientists argue that this exploratory drive will eventually take us to the stars. Despite the enormous challenges of interstellar travel, they believe humans will find ways to overcome them. Maybe not in our lifetimes, perhaps not for centuries, but eventually. Others are more skeptical, pointing out the physical limitations imposed by the laws of physics. The speed of light is an absolute barrier. Interstellar distances are so vast that even traveling at light speed, trips would take years or decades to the nearest stars, thousands or millions of years to reach distant parts of the galaxy. But Voyager offers a middle path. We may not send humans to other stars anytime soon, but we can send our robotic ambassadors. We can build spacecraft that explore for us, sending back data and images across the light years. Future probes might be far more sophisticated than Voyager, equipped with advanced artificial intelligence that allows them to make autonomous decisions. They might replicate themselves using materials found in asteroid belts or interstellar clouds, creating fleets of explorers that spread throughout the galaxy. This concept, called self-replicating probes or von Neumann probes after mathematician John von Neumann, who first proposed them, could theoretically explore the entire Milky Way galaxy in just a few million years. That sounds like a long time, but it's brief compared to the galaxy's age of 13 billion years. If such probes are possible, and if other civilizations have built them, why haven't we found any evidence of them? This question is part of the famous Fermi paradox, named after physicist Enrico Fermi, who asked, "Where is everybody?" The Fermi paradox observes that the galaxy is very old and very large. If intelligent life is common, and if even a tiny fraction of civilizations develop interstellar travel, the galaxy should be teeming with evidence of alien activity. Yet we see none. No alien megastructures, no obviously artificial signals from space, no self-replicating probes visiting our solar system. Why not? There are many proposed solutions to this paradox. Perhaps intelligent life is extremely rare and we're alone or nearly alone in the galaxy. Perhaps civilizations tend to destroy themselves before achieving interstellar travel. Perhaps interstellar travel is simply too difficult and no civilization has managed it. Perhaps aliens exist but choose not to contact us or make themselves obvious. Perhaps we're looking in the wrong ways or haven't been looking long enough. Voyager's journey into interstellar space adds an interesting dimension to this discussion. We now have direct measurements of the environment that any interstellar spacecraft must traverse. We know the density of matter, the strength of magnetic fields, the intensity of cosmic radiation. These measurements help us understand the challenges facing interstellar travel, not just theoretically but empirically. And the challenges are formidable. The interstellar medium, sparse as it is, becomes a barrier at high speeds. At 10% of light speed, collisions with hydrogen atoms release energy comparable to particle accelerators. The spacecraft would need shielding, but thick shielding adds mass, which requires more energy to accelerate. There's also the problem of propulsion. Chemical rockets, like those that launched Voyager, are hopelessly inadequate for interstellar missions. They're too slow and carry too much fuel relative to the payload. nuclear propulsion offers better performance. Fission reactors could power ion drives, accelerating spacecraft to higher speeds over long periods. Fusion rockets, if we can develop them, would be even better, offering higher exhaust velocities and more energy per unit of fuel. But even these advanced systems would take decades or centuries to reach nearby stars. For truly fast interstellar travel, we might need entirely different approaches. One idea is the laser sail. A large, ultra-thin reflective sail attached to a small probe could be pushed by powerful lasers from Earth orbit. The lasers would shine on the sail, transferring momentum through radiation pressure. With enough laser power, the probe could accelerate to a significant fraction of light speed. The Breakthrough Starshot initiative, funded by entrepreneur Yuri Milner and supported by Stephen Hawking before his death, aims to develop this technology. Their goal is to send tiny probes to Alpha Centauri within a generation. The challenges are immense. The sail must be incredibly light and reflective. The lasers must be powerful, requiring gigawatts of energy focused on a tiny target. The probe must be miniaturized to chip scale, carrying all necessary instruments in a package weighing just grams. Communication across light years with such a small antenna is nearly impossible, and there's no way to slow down once you arrive, so the probes would zip past their target at a significant fraction of light speed, with only minutes to gather data. Yet these challenges aren't insurmountable. Technology improves exponentially in many domains. The computers on Voyager were state-of-the-art in 1977 but are now hopelessly obsolete. Modern smartphones have millions of times more processing power and memory. Extrapolate that trend forward 50 years and imagine what might be possible. Miniaturization could produce incredibly capable probes, each containing sensors, cameras, computers, and communication systems in a package smaller than your fingernail. Another approach involves generation ships, massive spacecraft that house entire communities for journeys lasting centuries. The idea is that the people who launched the ship wouldn't live to see the destination. Their children, grandchildren, or even more distant descendants would be the ones to arrive. This raises profound ethical and practical questions. Would it be right to commit unborn generations to life aboard a spacecraft? How would the society aboard such a ship maintain cohesion and purpose over centuries? What psychological effects would confinement have? Science fiction explores these questions extensively, but they're not just fiction. If humanity survives long enough and decides to spread beyond our solar system, we'll face these dilemmas for real. Some scientists propose suspended animation or cryogenic freezing as solutions, allowing travelers to sleep through the journey. But we're nowhere near developing such technology for humans. Current cryogenic methods work for cells and small organisms, but reviving a frozen human without damage remains far beyond our capabilities. Perhaps the answer isn't biological travel at all. Maybe we'll send our consciousness instead of our bodies. Upload human minds into computers, then transmit the data at light speed to distant star systems where robots build new bodies or virtual environments. This idea raises even deeper questions about identity, consciousness, and what it means to be human. Would a digital copy of your mind be you, or would it be a separate entity that merely thinks it's you? These philosophical puzzles might seem abstract, but they're relevant to humanity's long-term future. Voyager's journey prompts us to think on cosmic timescales, to consider not just the next year or decade, but the next 1,000 or million years. What will humanity become? Will we spread throughout the galaxy or remain confined to Earth? Will we transform ourselves through genetic engineering or merge with artificial intelligence? Or will we destroy ourselves, leaving only silent probes like Voyager as evidence we ever existed? The discoveries Voyager made at the Heliopause connect to these larger questions. By understanding the boundary of our solar system, we understand both our protection and our prison. The heliosphere shields us, but also reminds us of our isolation. Beyond it lies the vast galactic wilderness, beautiful and dangerous, inviting and forbidding. It's an environment we barely understand, measured by just 2 spacecraft in a region that extends trillions upon trillions of miles in all directions. Consider the scale. The Milky Way galaxy contains somewhere between 100 billion and 400 billion stars. Most of these stars likely have planets. Recent discoveries by the Kepler Space Telescope and other instruments suggest that planets are common, with many stars hosting multiple worlds. Some of these planets orbit in the habitable zone, the region where temperatures allow liquid water to exist on the surface. Water is essential for life as we know it, so these habitable zone planets are prime candidates for extraterrestrial life. Yet even with billions of potentially habitable planets, the distances between them are staggering. The average distance between stars in our region of the galaxy is about 5 light years. That means light. Traveling at 186,000 miles per second takes 5 years to travel from one star to the next. Voyager, moving at about 38,000 miles per hour, would take about 75,000 years to cover that distance, and that's just to the nearest neighboring star, not to a specific target that might harbor life. The galaxy itself is 100,000 light-years across. The observable universe extends 46 billion light-years in all directions. These numbers are so large, they lose meaning. How do you comprehend 1 billion light-years? How do you visualize 1 trillion stars? The human mind evolved to navigate forests and savannas, to track animals and recognize faces. We're not equipped to intuitively grasp cosmic scales, yet we try. We build models and analogies. If the Sun were the size of a basketball, Earth would be a peppercorn orbiting 66 feet away. Neptune would be another peppercorn orbiting about half a mile away. The nearest star would be another basketball in Los Angeles if the Sun were in New York. The galaxy would extend beyond the solar system. The universe would be incomprehensibly vast, its true extent beyond any physical model. Voyager helps us bridge this conceptual gap. It's a tangible object built by human hands that has reached interstellar space. We can track its position, receive its signals, know exactly where it is and what it's measuring. It makes the abstract concrete. Interstellar space isn't just a theoretical concept anymore. It's a place we've visited, a frontier we've crossed, even if only with robotic explorers. The data Voyager sends back has practical scientific value, but it also has symbolic and inspirational value. It reminds us that we're capable of great things. When humans work together, when we pool our resources and knowledge toward ambitious goals, we can achieve what seems impossible. We can send spacecraft to the edge of the solar system and beyond. We can unravel the mysteries of nature. We can understand the universe itself. This understanding brings responsibility. As we learn more about our place in the cosmos, we realize how precious and fragile our situation is. Earth is the only known planet with life, the only world with forests and oceans, mountains and valleys, creatures that crawl and swim and fly. We're incredibly fortunate to live here, in this particular place and time, under this particular star. But this fortune isn't guaranteed to last. Cosmic threats are real. Asteroid impacts have caused mass extinctions in Earth's past and will happen again in the future. Supernovae could irradiate our planet if they occur close enough. Gamma-ray bursts from distant galaxies could strip away our ozone layer. These events are rare on human timescales but inevitable over geological time. Then there are threats of our own making: nuclear war, climate change, biological weapons, artificial intelligence gone wrong. Voyager's golden record acknowledges these dangers implicitly. By sending a message to potential alien civilizations, we're creating a backup, a record that might outlast our civilization even if we fail to survive. It's a sobering thought, but it's also empowering. We have the choice. We can work to address the threats we face, to build a sustainable civilization that lasts not just decades or centuries, but millennia or longer. Space exploration is part of that long-term vision. Not because we need to escape Earth, although having backup civilizations on other worlds would increase our chances of survival, but because the technologies and perspectives gained from exploring space help us here at home. Satellites monitor climate change, predict weather, enable global communication. Studying other planets teaches us about planetary science, helping us understand Earth's systems better. The inspiration from space missions motivates young people to pursue careers in science and engineering. Voyager exemplifies this inspiration. Countless scientists and engineers working today cite Voyager as the reason they chose their careers. They saw images of Jupiter's swirling storms or Saturn's magnificent rings and decided they wanted to be part of that exploration. They learned about the spacecraft's journey to the edge of the solar system and thought, I want to contribute to something like that. This inspiration is Voyager's legacy, perhaps even more important than its scientific discoveries. The mission also demonstrates international cooperation. While NASA led the project, scientists and engineers from many countries contributed. The Deep Space Network facilities that communicate with Voyager are located in California, Spain, and Australia, representing a global effort to maintain contact with our most distant explorer. Data from Voyager is freely shared with researchers worldwide. Publications based on Voyager measurements come from institutions across dozens of countries. Science at its best transcends borders, bringing humanity together in pursuit of shared understanding. This collaborative spirit is essential for tackling the biggest challenges facing humanity. Climate change doesn't respect national boundaries. Pandemics spread globally. Asteroid impacts would affect everyone. These problems require international cooperation to solve. Space exploration, by its nature, encourages this cooperation. When you're looking at Earth from space, you don't see borders. You see one interconnected system, one world that we all share. The overview effect, described by astronauts who've seen Earth from orbit, is a profound shift in perspective. They report feeling a deep sense of connection to all life on the planet, a recognition that we're all in this together, that national and ethnic differences seem trivial compared to our common humanity. Voyager's images, especially the pale blue dot, evoke similar feelings even for those who haven't traveled to space. We're all passengers on this small world, hurtling through the cosmos, completely dependent on the thin layer of atmosphere that separates life from the void. Voyager's discoveries about the heliopause reinforce this perspective. The boundary between our solar system and interstellar space is a protective barrier, but it's also permeable. Cosmic rays penetrate through, interstellar atoms drift in, the galaxy influences us constantly in subtle ways we're only beginning to understand. We're not isolated. We're part of the galaxy, connected to processes that occur on scales vastly larger than our planet or solar system. This connection extends backward in time as well. The atoms in your body were created in stars that died billions of years ago. The heavier elements, everything other than hydrogen and helium, were forged in stellar cores or supernova explosions. When these stars died, they scattered their contents across space. Those atoms drifted through the galaxy, eventually accumulating in clouds of gas and dust. One such cloud collapsed 5 billion years ago, forming our Sun and the planets around it. Earth condensed from that material, carrying within it the ashes of ancient stars. Life arose from these stellar ashes. Simple molecules combined into more complex ones. Chemistry became biochemistry. Self-replicating molecules emerged, then cells, then multicellular organisms. Evolution shaped life over billions of years, producing the incredible diversity we see today. And eventually, one lineage of primates developed consciousness, language, and technology. We became aware of our origins, capable of tracing our ancestry back through billions of years to the very beginning of the universe. This cosmic perspective, this awareness of our place in the grand sweep of time and space, is relatively recent. For most of human history, people believed Earth was the center of everything, that the universe was small and young, that humans were fundamentally different from the rest of nature. Science has progressively displaced us from this central position. Earth orbits the Sun, not vice versa. The Sun is one of hundreds of billions of stars in our galaxy. Our galaxy is one of trillions in the observable universe. We're not the center. We're inhabitants of a typical planet around a typical star in a typical galaxy. Some find this realization depressing. If we're so insignificant, if the universe is so vast and old, what does anything matter? But there's another way to look at it. Yes, we're small in cosmic terms, but we're also extraordinary. As far as we know, we're the only beings in the universe capable of understanding it. We're how the universe knows itself. The atoms that make up your brain were forged in stellar furnaces, scattered across space, and then arranged in such a way that they became conscious, capable of contemplating their own origins. Carl Sagan expressed this beautifully. The cosmos is within us. We are made of star stuff. We are a way for the universe to know itself. This isn't poetic exaggeration, it's literal truth. The carbon, oxygen, nitrogen, calcium, iron, and other elements in your body came from stars. The energy that powers your thoughts comes from the sun, captured by plants through photosynthesis, then transferred through the food chain. You're a temporary arrangement of atoms borrowed from the cosmos, destined to return to it eventually. But for now, those atoms are organized in such a way that they're reading these words, understanding ideas, feeling emotions. Voyager represents humanity's attempt to understand our cosmic context. By exploring the boundary of our solar system, we're learning about the environment that shaped us. The heliosphere has protected Earth for billions of years, allowing life to evolve without excessive radiation exposure. The solar wind that creates this protection comes from nuclear fusion in the sun's core, the same process that lights our days and warms our planet. Everything is connected in an intricate web of cause and effect, stretching across space and time. The magnetic fields Voyager measures tell stories of ancient processes. The interstellar magnetic field was shaped by supernova explosions, stellar winds, and the rotation of the galaxy itself. These fields guide cosmic rays, channel interstellar gas, and influence star formation. When the solar magnetic field meets the interstellar magnetic field at the heliopause, they interact in complex ways, creating the magnetic barrier Voyager 2 discovered. This barrier partially shields us from galactic cosmic rays, adding another layer to our cosmic protection. But these protective layers have varied throughout Earth's history. The sun's output has changed. Early in its life, the sun was dimmer than today, yet Earth somehow avoided freezing. This is called the faint young sun paradox. The explanation likely involves a thicker atmosphere with more greenhouse gases, compensating for reduced solar output. As the sun brightened over billions of years, Earth's atmosphere evolved, maintaining temperatures suitable for liquid water. The heliosphere's size has also varied. During periods of high solar activity, the solar wind strengthens, pushing the heliopause farther out. During solar minima, the heliosphere contracts. These variations affect cosmic ray exposure on Earth. Some researchers have proposed links between cosmic ray intensity and climate, suggesting that increased cosmic rays might enhance cloud formation, cooling the planet. The evidence for this connection is debated, but it's plausible that galactic processes influence terrestrial climate in subtle ways. Voyager's measurements provide baseline data for understanding these connections. By knowing the current state of the heliosphere and interstellar medium, scientists can build models to predict how things might change. These models help us understand not just our present situation, but also our past and future. What was the interstellar environment like when life first arose on Earth? How might it change as the solar system continues its orbit around the galaxy? These questions have implications for astrobiology, climate science, and our understanding of habitability. The concept of habitability extends beyond individual planets to entire regions of the galaxy. Some parts of the Milky Way are more hostile to life than others. Near the galactic center, stellar density is high, and supernova explosions are more frequent. The intense radiation environment might sterilize planets or prevent complex life from evolving. In the outer regions of the galaxy, there are fewer heavy elements, the building blocks of planets and life. Earth sits in the galactic habitable zone, far enough from the center to avoid excessive radiation, but close enough that heavy elements are abundant. Our location within this zone isn't permanent. The solar system orbits the galaxy, taking about 225 million years to complete one circuit. During this journey, we pass through different regions, including spiral arms, where star formation is active, and supernova explosions are more common. Some researchers have speculated that Earth's ice ages might correlate with passages through spiral arms, though the evidence is inconclusive. What's clear is that our galactic environment changes over time, and these changes can affect conditions on Earth. Voyager is measuring one specific moment in this ongoing journey. The data it collects represents a snapshot of the very local interstellar medium as it exists right now, in this particular region of the galaxy. In a few thousand years, the solar system will have moved far enough that the interstellar environment will be different. In millions of years, it could be dramatically different. Future civilizations, if they exist, might look back at Voyager's data as a historical record of what interstellar space was like in the early 21st century. This temporal dimension adds another layer to Voyager's significance. It's not just exploring space, but also creating a record of this moment in cosmic history. The Golden Record does this explicitly for human culture, but the scientific data does it implicitly for the cosmos. Future scientists, whether human or otherwise, might study Voyager's measurements to understand how the galaxy has evolved, how the interstellar medium has changed, how our corner of space compared to other regions or other times. The longevity of Voyager's physical presence in space is extraordinary. Unlike biological life, which decays rapidly, spacecraft can persist for enormous periods. Voyager's structure is made primarily of aluminum and other metals that don't corrode in the vacuum of space. There's no oxygen to rust iron, no water to cause erosion, no microorganisms to break down materials. The spacecraft will remain largely intact for millions of years, possibly billions, until it encounters something that destroys it or until the universe itself ends. This permanence is both humbling and exciting. Long after our civilization has either evolved into something unrecognizable or ceased to exist, Voyager will still be traveling through the galaxy. It will pass by distant stars whose light hasn't yet reached Earth. It might witness cosmic events we can't currently imagine. And if there are other intelligent beings out there, somewhere in the vastness of space and time, one of them might eventually encounter this strange artifact from an ancient civilization. What would they make of it? The Golden Record provides some explanation, with diagrams showing Earth's location and instructions for playing the record. But would an alien mind understand these symbols? Would they recognize the images as representations of a world and its inhabitants? Would they appreciate the music, or would it sound like meaningless noise? These questions are unanswerable, but they're worth pondering because they force us to think about communication, meaning, and the nature of intelligence itself. Human communication relies on shared context. When you read these words, you understand them because you've learned English, because you're familiar with the concepts being discussed, because you're a human with human experiences. But take away that shared context and communication becomes nearly impossible. How do you explain color to someone who's never seen? How do you convey emotion to something that might not feel emotions? The Golden Record attempts this across the ultimate communication barrier. Different species, different evolutionary histories, different sensory systems. The very act of sending this message reflects something profound about human nature. We're optimistic enough to believe in the possibility of connection, even across unimaginable distances and time spans. We're curious enough to want to introduce ourselves to the universe. We're humble enough to acknowledge that we might not be alone, that other minds might exist with their own perspectives and knowledge. And we're hopeful enough to think that any civilization advanced enough to find Voyager would also be wise enough to treat it with respect. Some critics argue that sending messages to potential alien civilizations is dangerous. What if they're hostile? What if revealing our location invites invasion? Stephen Hawking famously warned that contacting aliens might be like Native Americans encountering European colonizers, disastrous for the less advanced civilization. But Voyager's golden record is more like a message in a bottle than a deliberate communication. The chances of anyone finding it are infinitesimally small, and by the time they might find it, humanity will have been broadcasting radio and television signals into space for centuries, inadvertently announcing our presence to anyone listening. The reality is that interstellar contact, if it ever occurs, will likely not involve physical meetings. The distances are too vast, the travel times too long. More plausible is detection of alien signals or technological signatures. Projects like SETI, the Search for Extraterrestrial Intelligence, scan the sky for artificial radio transmissions or laser pulses. So far, they've found nothing definitive, but the search continues. With each passing year, our instruments become more sensitive, covering more frequencies and more of the sky. The absence of detected alien signals contributes to the Fermi paradox. If intelligent life is common, someone should have developed radio technology by now, and their signals should be detectable. The fact that we don't see obvious signs of alien civilization suggests either that intelligent life is extremely rare, or that civilizations don't last long enough to spread across the galaxy, or that they choose to remain silent, or that we're looking in the wrong ways. Voyager's journey doesn't directly address the Fermi paradox, but it does provide context. The challenges of interstellar travel are real and substantial. The environment between stars is harsh, the distance is enormous, the energy requirements staggering. Maybe other civilizations face the same barriers we do. Maybe they've sent their own robot explorers into space, and those explorers are currently drifting through the galaxy just as Voyager is, undetected and unnoticed because space is so vast and empty. Or maybe we're alone. Maybe intelligence is a rare accident, a fluke of evolution that occurred on Earth but nowhere else. The conditions necessary for complex life might be so specific, the evolutionary path so improbable, that we're the only technological civilization in the observable universe. This possibility, called the rare Earth hypothesis, suggests that simple microbial life might be common but intelligent. Technological life is extraordinarily unusual. If we are alone, it adds tremendous significance to our existence and tremendous responsibility to our actions. We would be the only part of the universe capable of understanding itself. Our extinction wouldn't just be a tragedy for humanity, but a cosmic loss, silencing the only voice capable of asking questions about existence, meaning, and purpose. This perspective suggests we should prioritize our survival, work harder to solve our problems, and take seriously the threats we face. But even if we're not alone, even if the galaxy teems with intelligent life, each civilization is precious and unique. Just as each species on Earth has intrinsic value regardless of how many other species exist, each intelligent civilization in the universe would have its own perspective, its own insights, its own contributions to make. Humanity's story, our art, music, science, and philosophy, our struggles and triumphs, are worth preserving simply because they're ours. Voyager embodies this impulse to preserve and share. The spacecraft itself will likely outlast our civilization. The golden record could potentially be played billions of years from now by beings we can't imagine, on worlds that don't yet exist. It's a message to the future, a testament that we were here, that we looked up at the stars and wondered, that we built machines to explore beyond our world, that we hoped for connection across the cosmic distances. The scientific instruments on Voyager serve a different but equally important purpose. They measure reality as it is without regard for human hopes or fears. The plasma wave instrument doesn't care about the Fermi paradox. It simply records the frequency of electron oscillations in the surrounding plasma. The magnetometer measures magnetic field strength and direction without interpreting what those measurements mean for human philosophy. This objective measurement is the foundation of science, the bedrock upon which our understanding of the universe is built. Yet humans interpret those measurements, find meaning in the data, construct theories to explain observations. Science is a human activity shaped by human curiosity and conducted by human minds. The questions we ask reflect our interests and concerns. Why do we care about the heliosphere's structure? Because it affects us, because it's part of our cosmic neighborhood, because understanding it helps us understand our place in the universe. Aliens, if they exist, might study entirely different phenomena, ask completely different questions, pursue knowledge for reasons we can't fathom. This diversity of perspective is valuable. Multiple viewpoints reveal aspects of reality that any single perspective might miss. In science, different researchers approaching the same problem from different angles often produce better understanding than any one approach alone. By analogy, multiple intelligent species studying the universe would collectively understand it better than any single species, even if they never directly communicate their findings to each other. Voyager's data contributes to humanity's understanding of the universe. The measurements of cosmic ray intensity, magnetic field strength, plasma density, and temperature at the heliopause are pieces of the cosmic puzzle. Other pieces come from telescopes observing distant galaxies, particle accelerators probing the nature of matter, gravitational wave detectors sensing ripples in spacetime, and countless other instruments and experiments. Gradually, piece by piece, we're constructing a comprehensive picture of reality. This picture reveals a universe of staggering complexity and beauty. At the smallest scales, quantum mechanics governs the behavior of particles in ways that seem bizarre and counterintuitive. Particles exist in superpositions of states, behaving sometimes like particles and sometimes like waves. They can be entangled with each other, correlated in ways that seem to violate common sense. Yet this strange quantum realm is the foundation of everything, the substrate upon which atoms, molecules, cells, and civilizations are built. At the largest scales, general relativity describes how matter and energy curve spacetime, creating what we experience as gravity. Massive objects like stars and planets warp the fabric of space around them, causing other objects to follow curved paths. Extreme curvatures create black holes, regions where space-time is so distorted that nothing, not even light, can escape. On cosmic scales, the expansion of the universe itself stretches space, carrying distant galaxies away from each other at speeds that can exceed the speed of light, though nothing travels through space faster than light. Between these extremes at human scales and the scales of planets and stars, classical physics describes motion, forces, energy, and thermodynamics with remarkable accuracy. The spacecraft engineering that enables Voyager's operation relies on these classical laws. The trajectory calculations, power management, communication protocols all follow predictable rules that engineers can model and control. Voyager operates at the intersection of these different scales and theories. Its instruments measure phenomena governed by plasma physics, electromagnetism, and thermodynamics. Its trajectory follows the laws of orbital mechanics and gravity. The data it collects helps scientists understand processes that range from atomic-scale interactions to galaxy-scale structures. This integration of knowledge across scales is one of science's greatest achievements, demonstrating that the universe operates according to consistent principles regardless of the size or complexity of the system being studied. The communication system that keeps us connected to Voyager is itself a marvel of engineering. The spacecraft transmits at about 23 watts, roughly the power of a refrigerator light bulb. This faint signal travels billions of miles through space, spreading out as it goes. By the time it reaches Earth, the signal is incredibly weak, about 10 quintillion times weaker than the power needed to run a digital watch. Yet the Deep Space Network's 70-meter dish antennas can detect it, separating Voyager's signal from cosmic background noise through sophisticated filtering and error correction. This communication link is our only connection to humanity's most distant explorer. Every day, ground controllers send commands and receive data, maintaining a conversation across distances that light takes over 22 hours to cross. When engineers send a command to Voyager 1, they wait nearly 2 days for confirmation that the command was received and executed. This delay requires careful planning and patience. You can't troubleshoot problems in real time when every exchange takes 2 days. The data Voyager transmits is precious. Each bit represents information about a region of space no other human-made instrument has visited. Scientists analyze this data, comparing it with predictions from theoretical models, discovering where the models are accurate and where they need refinement. This iterative process of prediction, observation, and revision is how science advances. Voyager's discoveries have prompted revisions to our understanding of the heliosphere, cosmic ray propagation, and the interstellar medium. But beyond the specific scientific findings, Voyager represents something larger, the human capacity for long-term thinking and ambitious projects. In an era often dominated by short-term concerns and immediate gratification, Voyager reminds us that we're capable of planning decades ahead, of investing in projects whose payoff extends far beyond quarterly earnings or election cycles. The engineers who built Voyager in the 1970s couldn't have known their spacecraft would still be operating in the 2020s. Yet they built it well enough that it has lasted. This long-term perspective is essential for addressing the challenges humanity faces. Climate change, for instance, unfolds over decades and centuries. The decisions we make today will affect conditions for our grandchildren and great-grandchildren. Similarly, space exploration is an investment in humanity's long-term future. The knowledge we gain, the technologies we develop, the inspiration we provide to future generations, all these benefits accrue over timescales longer than individual human lifetimes. Voyager's mission will eventually end. The plutonium in its radioisotope thermoelectric generators decays continuously, producing less heat and therefore less electricity each year. By the early 2030s, power levels will drop below the threshold needed to operate any instruments. Engineers will have to make difficult decisions about which instruments to turn off first, which to keep running until the very end. Eventually, perhaps around 2036 or so, Voyager will fall silent. The last signal will be received, the last data will be analyzed, and then nothing more. But the spacecraft will continue. It will coast through the void for millennia, gradually drifting away from the solar system. Its trajectory will carry it through regions of space no human instrument has measured, past stars that are currently just points of light in our telescopes. In 40,000 years, Voyager 1 will pass relatively close to another star system. In hundreds of thousands of years, it might pass through someone else's heliosphere, another star's protective bubble, though we'll never know because we'll have lost contact long before. The golden record will persist, its information encoded in patterns of grooves etched into gold-plated copper. Gold doesn't tarnish in space. The record could remain playable for billions of years, long after Earth itself has been consumed by the sun's expansion into a red giant, long after humanity has either spread across the galaxy or vanished entirely. It's a monument more permanent than any pyramid, any cathedral, any work of art we've created on Earth. Carl Sagan, reflecting on Voyager's golden record, wrote, "The spacecraft will be encountered and the record played only if there are advanced spacefaring civilizations in interstellar space. But the launching of this bottle into the cosmic ocean says something very hopeful. about life on this planet. He was right. The golden record says we're optimistic, curious, and ambitious. We believe in the possibility of connection. We value knowledge and exploration. We're willing to invest in projects whose benefits might never return to us directly. These are the qualities that make humanity remarkable, not our strength or speed, which pale compared to other animals, not our individual intelligence, which is impressive but not incomprehensibly superior to other primates, but our collective intelligence, our ability to accumulate knowledge across generations, our capacity for abstract thought and long-term planning, our drive to explore and understand. These qualities set us apart. We're the species that looked at the moon and decided to go there. We're the ones who wondered what lies beyond our solar system and built machines to find out. Voyager is one of those machines, and its journey continues. Right now, at this very moment, it's racing through interstellar space at over 38,000 miles per hour, farther from Earth than any human creation has ever traveled. Its instruments are measuring the environment, recording data that will be transmitted back to Earth for scientists to study. Its golden record is spinning slowly, carrying humanity's message through the darkness. The story of Voyager is far from over. As the spacecraft continues its journey, it will make new discoveries, encounter new phenomena, teach us things we can't yet anticipate, and even after it falls silent, its legacy will endure in the knowledge it provided, the inspiration it sparked, and the example it set. Voyager proves that we can accomplish extraordinary things when we work together toward ambitious goals. It shows that the universe is knowable, that mysteries can be solved through careful observation and rational thought. And it reminds us that we're all citizens of the cosmos, temporary residents of a small planet orbiting an ordinary star, but capable of reaching beyond ourselves to touch the infinite. The spacecraft's journey also highlights the sobering challenges of interstellar travel. Despite traveling for nearly 5 decades at tremendous speeds, Voyager has barely scratched the surface of the cosmic distances that separate stars. The nearest star system remains tens of thousands of years away at Voyager's current velocity. This reality raises profound questions about humanity's ability to truly explore beyond our solar system, to overcome the vast gulfs that separate us from other worlds. The physics of space travel, the immense energies required, and the fundamental limitations imposed by the speed of light all conspire to make the stars seem forever out of reach. If you made this far, make sure to subscribe to the channel and give a thumbs up. And if you're fascinated by the challenges that make interstellar travel so incredibly difficult, check out my video "This is Why We Are Stuck in the Solar System Forever" at the left side of the screen. It explores the hard limits physics places on our dreams of reaching the stars and why the cosmic ocean might be far more isolating than we'd like to believe. See you there.